Swayam Prabha. Digital India. Educated India.
Welcome friends to this second lecture of week 5 or module 5, and in this module we are talking about the ionization process in soil. And in the first lecture we have talked about what is ion exchange capacity of a soil and how this ion exchange capacity, which is a broad term, can be expressed as a summation of cationation capacity as well as an ionization capacity. Then we define what is cationation capacity and then what is ionization capacity. Remember, the cationation capacity of a soil is basically the capacity of the soil to exchange the adsorbed cation from its surface to the cations which are present in the surrounding solution, and ionization capacity is basically the opposite, that is the capability of exchanging the adsorbed anion to the surrounding anions in the soil solution. So, cation capacity basically depends on different types of clay minerals as well as organic matter. The clay minerals which have more permanent charge or producing the negatively charged surface, produces high cationation capacity. On the other hand, 1:1 type of clay mineral which shows variable charge basically is responsible for the ionization capacity. Amorphous minerals, they also shows the variable charge. When they develop the negative charge due to the surrounding solution pH, they contribute in cationation capacity, and when they are positively charged, they contribute into the ionization capacity. Organic matter largely contributes into the cationation capacity because of the development of negative charge onto the surface, and this cationation capacity and ionization capacity are both important. Generally, the cationation capacity is higher in case of soil than ionization capacity, and cationation capacity and ionization capacity are both important for soil to maintain the soil fertility, and because ionization capacity is also important for absorbing the negatively charged anions which are like sulphate, phosphate, which are responsible for the plant growth. Now, we have also seen that cationation capacity in the laboratory can be measured by both buffered method and unbuffered method. In the buffered method, it is somewhat exaggerate because of when we are trying this for a variable charge soils, and in case of that type of soil where the pH is less than 7 or 8.2, then the CEC which we are getting is basically the maximum CEC or potential CEC which we are getting. We are not getting the effective CEC. For getting the effective CEC, we have to go with the unbuffered method. Now, I have also showed you how we can measure or calculate the cationation capacity using the general step, using the general process of ammonium saturation, using two different methods. In first method, we have considered individual cations, and from their individual cation concentration in the leachate, we have converted them into milligram per kg, considering also the amount of soil which we have taken for leaching, and once we have converted them into milligram per kg of soil, then we converted them into centimole per kg of soil, and after that we multiply it with a valency to convert it to centimole charge. So, once we get the centimole charge of each and every cation, we basically took a sum of it and then we got the total CEC. Another method where we leach the adsorbed ammonium with the help of potassium, then this ammonium concentration in the leachate is measured, and therefore, they can be further converted into milligram per kg and then subsequently to the C mole charge per kg of soil. So, these are the two methods which we generally use, and in the laboratory we have also used the distillation method, where ammonium acetate solution, neutral normal ammonium acetate solution is used to leach the all the cations which are adsorbed, and once we saturate the soil with ammonium, then we we basically distill that ammonium, and in the form of ammonia gas in the presence of magnesium oxide or magnesia, and these evolved ammonia can be can be absorbed with an excess acid, and ultimately the unreacted acid can be measured by back titration with a standard alkali. From there we can calculate what is the amount of ammonia which has evolved, and from there we can get the measure of the CEC. Now, the next in this lecture we will be talking about the relationship between pH and CEC, and what is the what are the characteristics of ion exchange as far as the soil chemistry is concerned. Now, pH and CEC, generally we know that CEC increases with the pH. Obviously, the permanent charge of 2:1, the permanent charge of 2:1, pH dependent charge of humus and allophane and some 1:1 type of clay hold the exchangeable ions. Now, although the permanent charge does not depend on the pH dependent charge depend on the surrounding pH. So, if we increase the pH of the surrounding solution, the pH dependent charge develop negative charge, and these negative charge attract more and more cations, and these negative charge develop both in 1:1 type of clay, amorphous clay minerals like allophane, or it can be produced by humus, because most of the negative charge which is produced by the humus are variable charge. So, ultimately these all are responsible for catenation capacity. So, as the pH is raised, the negative charge on some 1:1 type of silicate and allophanes, humus, and even iron aluminum oxide increases, and CEC also increases. In alkaline condition, CEC reflects the pH dependent charge as well as the permanent one. So, in the alkaline condition, when we are increasing the pH, this CEC basically reflects the pH dependent charge as well as the permanent charge. So, that is why when we are using the buffered method in the alkaline condition, it shows the potential or maximum CEC, not the effective CEC, because it measures the CEC which is responsible for the which is responsible for the permanent charge, as well as the CEC which is generating from the variable charge surface. Now, exchangeable cations in the field soils. What are the exchangeable cations in the field soils? The exchangeable ions in soils depends upon the climatic condition. For example, if we consider iron aluminum, complex aluminum hydroxy ion H plus ion, they are the most prominent cations in humid region, where we see extensive leaching of the soil or weathering of the soil. So, in the highly weathered soil and warm and humid climate, you will see the dominance of iron aluminum, complex aluminum hydroxy ions and protons. And in the case of low rainfall areas or arid and semi-arid region, we will see the dominance of calcium, magnesium and sodium. So, in a given soil, the proportion of the cation exchange capacity, so in a given soil, the proportion of the cation exchange capacity satisfied by a particular cation is termed as a saturation percentage for that cation. This is a very important term. In other words, the saturation percentage of a cation is represented by the fraction of the catenation capacity which is explained by that particular cation. So, if 50% of the CEC is satisfied by the calcium ions, the exchange complex is said to have a calcium saturation percentage of 50. And this terminology is especially useful in identifying the relative proportion of sources of acidity and alkalinity in the soil solution. So, this saturation percentage is very important, and we will see another important term, base saturation percentage, in the coming lecture. So, if we move ahead, we can see this table, and this table shows a very important trend. The cation exchange capacity property is typical for unamended clay loam surface soil in different climatic regions. So, you can see here there are 4 different climatic conditions: warm and humid climatic region, cool and humid region, semi-arid region and arid region. So, you can see exchangeable H plus, Al3 plus, percentage of Cc which is occupied by these exchangeable H plus and Al3 plus is highest in case of warm and humid climate, and as we go from this warm and humid climate to arid region, we are getting further decrease. And in case of exchangeable calcium and magnesium, as we are going from the warm and humid climate to arid region, we are getting a constant increase. Exchangeable sodium, in case of warm humid climate, it is trace concentration. In case of cool humid region, it is only 0.02, that is only 0.1%. In case of semi arid region, we can get 4%, and in case of arid region, we are getting 19%. So, that basically again shows that how these saturation percentage of different ions changes depending on the surrounding climatic condition. So, now cation saturation and nutrient availability. You know that if the percent saturation of some ions are high, then those ions will be easily and rapidly displaceable. So, obviously the percent saturation of some ions are high means they have higher catenation capacity. So, they will be easily and readily displaceable. So, influence of complementary cation, so the strength of adsorption of common cations on most soil colloids follows this particular order, where Al3 plus which is greater than Ca2 plus which is further greater than magnesium. Potassium ammonium has similar affinity to the surface which is further greater than sodium. So, K plus can be easily replaced by aluminum ions in the acid soil, and it will be available for the plants. So, there is some nutrient antagonism. So, there is some nutrient antagonism which is generally originating from this selective affinity for or selective strength of adsorption. So, there are some nutrient antagonism that in certain soil cause inhibition of uptake of some certain nutrient by the plant. For example, when there is a high potassium level, it can limit the uptake of magnesium. Okay. So, that says even when the significant quantities of magnesium are present in the soil. So, that shows the nutrient antagonism, because what is the reason behind that? You can see magnesium has more affinity than that of potassium. So, if the soil is saturated in this exchange complex is saturated by potassium ion, if we add magnesium ions, then the magnesium will replace the potassium, and this potassium will, although the potassium will be come into the soil solution, the magnesium will get adsorbed into the surface tightly, and as a result there will be nutrient antagonism. So, high potassium levels in the soil solution limit the uptake of magnesium, because magnesium get adsorbed by replacing the potassium in the exchange complex. Another important thing you can see here in this picture, there are two different conditions. So, the half circles, so this is basically colloidal surface, and these are adsorbed cations, and this is basically root exuding H plus ions to exchange with the cations on the colloids. And you can see the half circles are basically, so this is a half circle, 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 this is a half circle. So, these half circles are loosely held with the soil, and the root will take cations from the soil in exchange with the H plus ion. So, this H plus ion they replace with this Na and this potassium, and so they basically make an exchange with this sodium and potassium. So, in the left figure, in this figure you can see the loosely held sodium ions. So, the sodium is loosely held will be easily taken up by the plant. So, it can be easily taken up by the plant. In the right figure, the K plus will be easily taken up by the plant, and the K plus will be comparatively more vulnerable to be replaced and sent to the soil solution. So, K plus will be more available for the plant uptake and leaching. What is the reason behind that? The reason is the sodium and potassium has very low affinity to be adsorbed into the exchange complex of a negatively charged colloid. As a result, they are easily amenable for replacement with H plus ion, which is generating from the root exudates, and as a result this potassium goes to the soil solution and then available for the plant to uptake them and for further leaching. Okay. So, what is the anion exchange and adsorption mechanism? So, the basic principle of anion exchange are similar to those of cation exchange. So, the charge on the colloid are positive and the exchange among negatively charged cations. So, you know the positive charge associated with the surface of kaolinite, iron and aluminum oxides and olefin attract anions such as sulphate and nitrate. So, here you can see that this is a colloid surface which is positively charged colloid surface. Let us assume this is 1:1 type of kaolinite which is attached with these nitrate anions. So, if we add this chloride, then chloride will replace this nitrate. So, this is an example of anion exchange reaction. So, just as in the case of cation exchange, equivalent quantities of nitrate and chloride are exchanged in this condition. Okay. So, the reaction can be reversed and nutrient anions so released can be absorbed by the plant. So, this nitrate which is released by this clay colloid can be further absorbed by the plants. So, we know that cation exchange capacity increases with the increase in pH, because when you increase the pH, the pH dependent charge surface, the pH dependent charge produces the negative charge into the clay surface. As a result, it will attract further more cations into the clay surface. So, cation exchange capacity will increase. Opposite trend can be found in case of anion exchange capacity, because as we increase the pH, there will be generation of negative charge surface, and negative charge surface will repel the anions which are also negatively charged. As a result of that, the anion exchange capacity will further go down. So, with the increase of pH, the trend of CEC and EEC are basically just opposite to each other. Now, let us see what are the characteristics of the ion exchange. So, ion exchange involves the electrostatic interaction between a counter ion in the boundary layer between the solution and a charged particle surface and counter ions in a diffuse cloud around the charged particles. So, obviously, this ion exchange is basically the electrostatic interaction between a counter ion. So, let us consider it as a positively charged cations in the boundary layer between the solution and the charged particles, obviously, of the surface charge of the particle surface and counter ions in a diffuse cloud. So, whatever counter ion which are adsorbed into the surface of the negatively charged colloid will be replaced by the same counter by the counter ions which are present in the diffuse layer. So, if it is usually very rapid and basically diffusion controlled, reversible in nature and stoichiometric, and in most of the cases there is some selectivity of one ion over the another by the exchange surface. Obviously, just like in case of cation exchange capacity, anion exchange capacity also shows the selectivity among different anions. So, exchange is reversible, exchange reversibility is indicated when the exchange isotherm for the forward and backward exchange reaction basically coincide, and exchange irreversibility or hysteresis is sometimes also observed. So, these are some these are some aberrations, these are some special condition where we can see exchange irreversibility or hysteresis and that has been attributed to the colloidal, and these exchange irreversibility or hysteresis can be attributed to the colloid aggregation and the formation of the quasi crystals in the soil. Now, we have discussed couple of times about the stoichiometry. However, let me again discuss the stoichiometry. Stoichiometry here means that any ions, in the context of ion exchange, stoichiometry means that any ion that leave the colloidal surface are replaced by an equivalent amount of other ions. Again, any ion that leave the colloidal surface are replaced by an equivalent amount of other ions. This is the definition of stoichiometry as far as the ion exchange is concerned. Now, the electrostatic forces are involved in ion exchange. Coulomb's law can be invoked to explain the selectivity of the preferences of the ion exchanger for one ion over another. Now, for a given group of elements with the same valence, the ion with the smallest hydrated radius will be preferred. For the group 1, for example, in case of group 1 minerals elements, the general order of the selectivity will be cesium will be will have more affinity than rubidium, then potassium, then sodium, then lithium, then H plus. Because in case of cesium, the ions has the smallest hydrated radius. As a result of that, the thickness of the thickness of the diffuse double layer is also very less in case of cesium, and there the attraction is more in case of cesium than rubidium, potassium, sodium, lithium, which have more hydrated radius. When there is a more hydrated radius, the diffuse double layer thickness also increases. So, if ions have different valences, then higher the charge ion will be preferred. For example, Al3 plus will have more affinity than calcium, magnesium, and potassium and ammonium, which is have further more affinity than the sodium. So, here sodium has the least affinity. So, that is why in the root example I showed you that sodium and potassium can be easily replaced by the H plus ions. However, this Al3 calcium has more affinity to the charged surface. Now, in examining the effect of valence on selectivity, polarization is another important aspect. So, if we consider this, polarization is basically the distortion of the electron cloud about an anion by a cation. So, here you can see this is an idealized ion pair of the both positive ion and the negative ion, cation and anion with the similar size, almost similar size. So, progressively you can see as we go in this direction, progressively the size of the anions is getting lower. So, the smaller of the hydrated radius of the cations, the greater is the polarization. Obviously, you can see as it is getting smaller, there is more and more polarization, and due to the distortion of the electron cloud about an anion by a cation. So, as we go from this idealized ion pair to mutually polarized ion pair to this polarized ion pair. So, we can see the polarization increases, and the greater is the valence, the greater is the polarizing power. So, as we decrease the cation size, the polarization increase, and with the anions, the larger they are, the more easily they can be polarized, and also the greater is the valence, the greater is the polarizing power. So, this polarization has a very important effect on the ion exchange property. Now, selectivity sequence or lyotropic series for some of the common cations follow this order. So, you can see barium followed by lead and strontium, then calcium, nickel, cadmium, copper, cobalt, zinc, magnesium, argentum, cesium, rubidium, potassium, ammonium, sodium and lithium. So, lithium has the least selectivity, however, barium has the highest selectivity. So, in case of clay mineral, obviously kaolinite has the external exchange site which are that are present, and rate of ion exchange is rapid. In case of 2:1 type of mineral contain both external and internal exchange site, for example vermiculite, and in case of micas. Now, if we consider CECs of different soils, obviously sandy soil has lower CEC, but clay soil has high CEC values, because sandy soil, the sands are electrically neutral, they do not produce charge. As a result, they are electrically neutral. As a result, they have no or very low CEC. Iron aluminum oxides, in case of iron aluminum oxides, kaolinite are having low CEC, which is less than 10 centimole charge per kg. In case of mica and chlorides, they have 10 to 40 centimole charge per kg. In case of smectite and vermiculite, they ranges from 80 to 180 centimole charge per kg, and humus is having the highest CEC, that is greater than 250 centimole charge per kg. So, you can see that humus or organic matter shows couple of fold higher cation exchange capacity than the crystalline clay minerals. Smectite and vermiculite shows the high cation exchange capacity. However, iron aluminum oxide shows the low cation, kaolinite shows the low cation exchange capacity, because generally they do not produce very high negative charge. Their charge is pH dependent. Mica and chlorides produce also very low charge. So, at higher pH, the soil humus basically contributes more CEC to the soil with a constant amount of clay. Obviously, as the pH increases, there will be more dissociation of the carboxyl group, as well as the phenolic the aromatic carboxyl group, as well as the phenolic group of the organic matter, which will attract more cations. So, obviously that will increase the cation exchange capacity. So, higher pH will soil humus will contributes more CEC to the soil with a constant amount of clay, because in case of clay the permanent charge does not vary with the surrounding pH. So, at pH 4 to 4.5, 1 gram of soil humus increases the CEC of 0.13 centimole charge per kg. However, at pH 5.5 to 5, it increases almost double, that is 0.26 centimole charge per kg. So, you can see here, this is more clear in this graph, where we are increasing the organic carbon in the x axis and the cation exchange capacity. So, the two conditions, when you are increasing the organic carbon concentration, the cation exchange capacity increases, and this increase is low in case of lower pH, intermediate this is for intermediate pH and this is for higher pH. More pH means more dissociation of the aromatic carboxylic group or phenolic groups, and more dissociation of the groups means more negative charge. More negative charge means more attraction of the opposite counter charge or positive charge cation, that means more CEC. So, this table basically shows the CEC of different secondary minerals. So, you can see kaolinite has only 2 to 15 centimole per kg, whereas halloysite has 10 to 40, talc has less than 1, montmolybdenum 80 to 150, dioctahedral vermiculite 10 to 150, trioctahedral vermiculite 100 to 200, muscovite 10 to 40, biotite 10 to 40, chloride 10 to 40, and allophane from 5 to 350. Now, allophane produce more variable CEC, because it does not have any specific crystalline structure. Now, in case of kaolinite, CEC of a secondary clay minerals. Now, in case of kaolinite, the CEC of a kaolinite varies depending on the impurity present in it. So, if the impurity is present, its CEC as low as less than, it shows the CEC of as low as less than 2 centimole per kg, as pure kaolinite has very less isomorphic substitution. So, pure kaolinite does not have isomorphic substitution, because there is no as a result there is no negative charge development. Only CEC can be shown when there is an impurity. So, that CEC is also very low, that is less than 2 centimole per kg. Negative charge resulting from surface functional edge groups such as aluminum hydroxide, which are deprotonated with the neutral pH extracting solutions such as ammonium acetate, cause unexpected variation in CEC measurement. Again, negative charge resulting from surface functional edge groups such as aluminum hydroxide, which are deprotonated with the neutral pH extracting solution, cause unexpected variation in CEC measurement. Obviously, these variable charge surface, when we add different solution, the variable charge surface create different types of unexpected variation. In case of kaolinite, we know that this is the structure of the kaolinite, and in the structure of the kaolinite, it can be shown that there is no isomorphous substitution. As a result, there is no negative charge development. Here you can see this is 1:1 type of layer, where one silica tetrahedra sheet is attached to the one aluminum octahedra sheet by sharing the apical oxygens, and the d axis spacing is 0.74 nanometer and d axis spacing is 74 nanometer, and you can see one thing that due to the absence of isomorphous substitution, there is no permanent charge development. Only the permanent charge develop in case of I am sorry, there is no permanent charge development, only the CEC can be seen, very low CEC can be seen around 2 centimole charge per kg when there is some impurity. When there is an impurity, we can see some charge development. In case of vermiculite, dioctahedral vermiculite has more layer charge than smectite, but less cation capacity due to the presence of potassium ions in its interlayer. Remember that potassium it has a smaller hydration radius and it fits snugly into the interlayer space. The attraction between the K plus and clay's interlayer surface is more, hence it is less available for exchange, and presence of aluminum hydroxide in interlayer also reduces the catenation capacity by blocking any exchange site, such as in case of chlorite. And trioctahedral vermiculite has calcium and magnesium in its interlayer, hence more CEC. In case of trioctahedral vermiculite, we can see more CEC than dioctahedral vermiculite, as this calcium and magnesium have no restriction for cation exchange. So, structure of vermiculite, it has the highest catenation capacity of all clays. It has the less swelling capacity than smectite, but more than that of kaolinite. It is nutrient rich because of high catenation capacity, and it is stable under low pH conditions. So, guys, you have seen something important information in this lecture. We have discussed the practical implication of catenation capacity and its properties, and how this catenation capacity and catenation capacity shows different affinity for different ions, and what are the reason for this variation in their affinity we have discussed, and also depending on the structure of different clay minerals, how this catenation capacity varies we have seen. So, I hope that you have seen some useful information in this lecture. Let us meet in our third lecture of week 5 to discuss different other aspects of ion exchange phenomena in soils. Thank you very much.